So today we're going to take a look at finding volume of solids of revolution. I did post a link for a couple of things for you guys to take a look at if you want some help kind of visualizing what we're talking about. We are talking about taking 2D regions and rotating them around a horizontal axis and finding the volume of the solid that would be created if we did that. Okay, I will tell you guys that a lot of times the most difficult part for a lot of students is trying to visualize what these look like. But I'm here to tell you that you don't have to actually be able to visualize these in order to be able to solve the problem. So if you are really struggling and that didn't help you looking at those other links, please don't feel bad because you're still going to be able to do these problems. Okay. I just like to try to offer some visuals for those of you who would really like to try to see what this looks like. And sometimes it really does help just being able to kind of picture what this is going to look like if you were to rotate it. One of the biggest things that's important when we are rotating especially with rotating around a horizontal axis, is figuring out whether or not we have empty space between the region that we're rotating and the line of rotation. That's going to decide whether or not we're using disk or washer method. Now, disk or washer method, they're the same type of method. They use the same idea. It's just that with a washer method, you have empty space between your area you're rotating and the line of rotation. Okay, so take a look at this first picture. We're taking the area between A and B of some region, whatever this function is, okay, and we are going to rotate that around the x-axis. If we take that region, there's no empty space, okay, there's no empty space because we're bounded by the x-axis here. So there's no empty space in between the region that we're rotating and the line of rotation, which is the x-axis. So we can use what's called disk method. Basically, what we want to think about, remember we talked about way back before when we did related rates, we noticed that some of the volumes, when we took the derivative, we got area, most notably with surface area and volume of a sphere. You take the derivative of the volume and you get the surface area. So it kind of harkens back to that idea. We can get the accumulation of the area to find the volume, okay, going the other way when we take an integral. So if we have this disk method where we have no empty space, think about taking a cross section. If you cut right through this, you would have a circle, right? And the area of a circle is pi r squared. The only thing that might be changing is your actual radius, which depends on the function, right? A lot of times we're talking about upper minus lower, which again goes back to our area section where we found area between curves. Okay, so we want to take the integral of the area of that disk over the interval that we have the area for from A to B. So we have pi. We usually pull the constant out front just because it's easier to write it that way. Pi times integral from A to B of r squared, whatever that r may be. Now, take a look at this other example over here. This is the washer method. Okay, we still have a region from A to B, but the difference is that now the bottom of that region, okay, look at the difference between the bottom of the region and the line of rotation. If we're rotating around the x-axis this time, notice that we're going to have some empty space between that bottom of the region and the line of rotation. So this is why it's called a washer. If we were to cut a cross section out, notice, look at this picture at the end. We would have a circular region in the middle that we would have a washer. So we would have a circular region in the middle where we didn't have any volume because there's no area there to rotate. So we have to think about taking the area of the larger circle and subtracting the area of the smaller circle, and that's what we're taking the integral of. So that's why we have big R squared minus little r squared. Big R, okay, so big R is the distance from the line of rotation to the furthest part away. Okay, notice this would be an example of the big R. And then little r, Let's find a different color, maybe green. Little r is the distance from the line of rotation to the closest edge of the area that we're rotating. Notice that the little r in this case is the same because it's to that horizontal line, okay, whatever that amount may be. But that's not always going to be the same. Let's take a look at some examples so that we can start to figure out how to use this. Okay. All right. So example 1, find the volume generated when the region bounded by y equals 2x, y equals 0, and x equals 3 is rotated about, and then we've got a couple different places we're going to rotate. So first thing I'm going to do is draw a picture. So y equals 2x, we have a linear function. It goes through the origin, has a slope of 2. Y equals 0. Y equals 0 is the x-axis, and x equals 3. So this is the region we're talking about. Okay. This is the region we're talking about rotating. Okay. Now, if we rotate around the x-axis, we have no empty space, so we are using the disk method. Okay. So we need pi times the integral, and we need our interval. We are starting at 0 and we're going to 3. So integral from 0 to 3 of the radius squared. Now the radius would be different depending on where we're at as far as an x value. Think about this. The radius is dependent upon this function. So the radius is that actual function. In this case, the distance from the x-axis, the line of rotation, to the edge of the area is always whatever that function is, 2x. Okay, so in this case, I'm just going to write it down here so that we've said it. Big R is 2x. So we need 2x squared. Now, we could do this one by hand, but because we're interested in being quicker and trying to get to these answers quicker, I would just go ahead and put it in the calculator. Okay, integral of 2x all squared, comma x, comma 0, comma 3, and then I need to remember to multiply by pi. So that would be my total area, total volume would be either 36 pi or approximately 113.097. Okay, that's your volume of that solid that would be generated if we revolved around the x-axis. Okay, now let's take a look at this next one. Now we're going around the line y equals 6, which is a horizontal line up here. So if we go around this line, we're going to have empty space in between this region and the line of rotation. We're going to have some empty space. So this is using washer method. Okay. Now with washer, we need to find big R and little r, right? Okay. Big R is going from the line of rotation to the furthest part away of the region. So if we start at 6 and we go to the furthest part away, every time we're going to 0. Okay, so big R would actually be 6. Little r, we'd be starting at the line of rotation and going to the closest part. So we're just going right here every time for little r. So that would be 6 minus whatever 2x is. So little r is 6 minus 2x. So to find our volume, we want pi times integral from 0 to 3. It's still the same interval of big R squared. So 6 squared minus little r squared, 6 minus 2x squared. Okay, let's find that. Okay, so we want integral of 6 squared minus 6 minus 2x squared, comma x, comma 0, comma, oops, that's not an x, comma 0, comma 3. Okay, and we got to multiply by pi, so that would be 72 pi, or approximately 226.195. Well, that doesn't look like a 6, but it is. There we go. Okay. Now, let's take a look at one that's a little bit more. Now we're looking at the region bounded by y equals x squared. Okay, so we've got y equals x squared. We've got a parabola. The line y equals 0, which is your x-axis again, and the horizontal line or vertical line x equals 2. Okay, so we are going around the x-axis to begin with. That's the disk method. We have no empty space. Right, and I'm moving stuff around. That is not what I intended to do. So we're moving, we're going around the x-axis, and we have no empty space. So now we need to use disk method. We need to find our big R. That's only one R for disk method. So let's take a look. We want to go from line of rotation to the edge of the area. If we do that every time, it's just wherever the function is. So our big R, if I could write, come on. Big R is x squared, the function. So we want pi times the integral from 0 to 2. This time we're going from 0 to 2 of big R squared. So x squared squared. If we take that integral, we have, that'll be x to the 4th. We could go ahead and just put it in as x to the 4th. Save a little bit of time. And then comma x, comma 0, comma 2. Okay, so that's 6.4 pi. Okay, 6.4, of course, is 32 over 5. So we could call this 32 pi over 5, or as a decimal, 20.106. Okay, now let's take a look at part B. We're going around the line y equals 4, a horizontal line up here. So we're using washer. Our big R from the line of rotation to the furthest part away every time would be 4. Our little r from the line of rotation to the closer edge of the area would be 4 minus x squared. So if we set this one up, we have pi times the integral from 0 to 2, still the same interval, of big R squared, so 4 squared, minus little r squared, 4 minus x squared, all squared. So let's find that. Okay, integral of 4 squared minus 4 minus x squared, all squared. Oops, I need my squared. All squared, comma x, comma 0, comma 2. Okay, as a decimal, as a decimal, we gotta still need to multiply by pi, but let's find the fraction of this. So this is 224 over 15 pi, or as a decimal, 46.914. Okay, again, both answers would be acceptable. It just depends on what type of problem you have. Okay, if it was multiple choice, it would depend on the problem, whether it was calculator active or inactive. This would most likely be calculator active. Okay, but again, they could express the answer either way. All right, let's try one more. This time we're looking at the region bounded by x squared and x cubed. Actually, I don't need such a big. Okay, so x squared and x cubed. I'm actually gonna just make it smaller. On this one, okay, there's our x cubed. Okay, and then we need our x squared. All right, so we know these are equal to each other at 0 and 1. That's going to be our interval. Okay. Also, let's start to think about a few things. A lot of times people get confused about what's above and below here. If you want to just take a number between 0 and 1 really quick and plug it in, say 1/2. If we were to plug in 1/2 into x squared, we'd get 1/4. Into x cubed, we'd get 1/8. So on this interval from 0 to 1, we know that x squared is above x cubed. Okay, so it's the upper of the area of your region. Just so you know that. For rotating around the x-axis, now we're actually going to have some empty space, so we actually have to use washer here. Our big R is going to be distance from line of rotation to the furthest part of the region every time that's going up to x squared, the upper function. Our little r, distance from line of rotation to the lower end of the area, would be going up to x cubed every time. So our volume would be pi times the integral from 0 to 1 of x squared minus x cubed squared. Okay, big R squared minus little r squared. Let's go and find that. Okay, so that's going to be x to the 4th minus x to the 6th. Just go ahead and simplify a little bit. You don't have to do that, but I think that goes in a little bit faster. From 0 to 1. And that gives us 2 over 35. Okay, and that's times pi. So 2 pi over 35, which as a decimal, I'm assuming it's going to be pretty small. 0.1795, so 0.180. Okay. Again, either one is acceptable if it's calculator active. And if it's multiple choice, they could do it either way. All right. So part B, the line y equals 2. So now we're looking at horizontal line above for, again, washer, because there's going to be empty space. Big R, distance from the line of rotation to the furthest part away, to the further end of the region. We're going from that line of rotation down to x cubed, because that's at the bottom. That's the furthest part away. So we're taking 2 minus x cubed. For little r, we're going from line of rotation to the closer edge of the area. So that's going from 2 down to x squared. So that's 2 minus x squared as little r. So let's set this up. Pi times the integral from 0 to 1 of 2 minus x cubed squared minus 2 minus x squared squared. Okay, let's go to our calculator. Let's get our integral. We want to do 2 minus x cubed all squared minus 2 minus x squared all squared, comma, x, comma, 0, comma, 1. Okay, as a fraction, this is 29 pi over 105. As a decimal, let's find what that is. .868. Okay, so again, depending on what type of problem it is, you may have a fraction form or you may have a decimal form. Guys, we're going to do a lot of practice with this. I would always keep in mind that you're looking at the distance from your line of rotation to the furthest part away for your big R, distance from line of rotation to the closer part for your little r. Okay, if your line of rotation is above the area, then you're going to take the line amount minus that furthest part away. For big R, you're going to take the number minus the closer part for little r. If your line of rotation is below the region, then you may end up adding something. Okay, it just depends on where it is. But you're always, again, referencing the line of rotation to the furthest part away of the area of the region to find the big R, and you're referencing the line of rotation to the closer part of the area of the region for the little r. Okay, it's a lot easier when we have no empty space, but a lot of times you do end up with empty space and have to use the washer method.